again we discussed what kinds of transformations you can make on the basis vectors. You can go from one basis to another basis, right? Because I mean there's nothing unique about it. I may choose one basis, you may choose another basis, right? And then we found out what is the relation between these different bases. Okay. One little thing, remember I was choosing some basis vectors, say I, where I goes from 1 up to n. So this is some basis vectors. But I could also have chosen another basis vector, which I called like that. Again, I goes from 1 to n, where n is a dimension of the vector space. Vector space, I will always use capital S for vector space. And then since this is a basis vector, I can expand every single vector here in terms of as linear combinations of that, right? And then I use the I wrote it like this: I j j summed over j, right? So one just to in the book, in this book, instead of a, the symbol which is used is r. Okay, just a symbol. I mean, so I will just stick with the same symbols that are used in the book. Okay, so that is one thing. And second thing, remember that this is I goes from 1 to n, because this I goes from 1 to n. There are n equations here, right? The I labels the equations, and j, there's a summation index here. So j also goes from 1 to n. Okay, so this I can think of it as a n by n matrix. This R, I can think of it as a n by n matrix whose entries are, the row and column entries are given by Rij, right? And then I mentioned to you that there is a, I mean, it's up to you to choose your convention. Either you can think of this as labeling the row or that as labeling the row, right? Now in the book, the convention that is used is I mean j labels the row and I labels the column. Okay, so again I will follow the same convention that is in the book. It's a matter of convention, but we stick with the same conventions. So this is the row and that's the column. And in this case, if I take any vector, say a, I can expand in this basis, which will be ai summed over I, and I can also expand the same vector in this basis. Okay, it will be I prime with some different coefficients. Okay, and then we found the relation between these two. Right, given this matrix R, we can find the relation between these two. Right? And the relation was simply A prime. I mean, in the matrix notation, A prime is simply R inverse A, where A and A prime, we think of it as column vectors. So by A, I mean A1, A2, A3, AN, right? You put all these numbers in one column, right? Similarly, A prime will be A prime 1, A prime 1, A2 prime, and so on, AN prime. Then we have this relation. Okay.
Question.
Yeah.
So when you write it in that notation, that A stands for the coefficient.
These A's are the coefficients, right?
So even in the example that we did in class, the V was the coefficient.
Yes, yes.
Then the I, in that case, we assume the I is a vector.
Okay, so this is of course a vector. I mean, when we said this is a linearly independent set of vectors, right? So of course this I belongs to S, right? Similarly, I prime is also a linearly independent set of vectors. So I prime also belongs to S. So these are all vectors. These are all elements of S. These are numbers. These AIs and A prime I's are numbers, right? If it's a complex vector space, this will be complex numbers. If it's a real vector space, this will be real numbers. So these are just numbers. And now I put all these numbers, arrange them, and write it as a column vector, right? Either it will be a real column vector or a complex column vector, depending on whether it's a real vector space or a complex vector space. Okay. And then the relation between these two, between the A primes and A's, is given by this equation, where this is simply a matrix multiplication. Okay. or you can just invert it, A is equal to R A prime. So, if I want to write it explicitly in terms of these labels, what it says is that AI is equal to R I J A prime J, summed over J, to write it explicitly. Its matrix notation is useful because, I mean, this is such a simple looking equation. You don't have to worry about the indices and so on and so forth, right? Whereas here you have to explicitly write down the indices. So whenever you can write down some matrix equation, it's easier, easier to manipulate and so on. So many times we will do that. We will first obtain the equations in the index notation, and then we will try to rewrite it in a matrix language. Okay, that we'll try to do. Okay, so this is my main point was that the reason why I chose this sequence was because in all of these steps I have only used the vector space structure, nothing else. Okay, today we will start talking about a little bit more. We'll put in some more structure in the vector space. In particular, the scalar product. You are familiar with in the plane, in the example of plane. If I give you two vectors, let's say A and B. Now I use the vector notation, right? In this example, I'll always use the vector notation with the arrow. Right? Then I know what I mean by A dot B, right? I mean, so this is defined. What is the meaning of this? I mean, what it is saying. Okay, so what is it going to be? This will be some real number, right? It's a real number. So what it is saying is that if I give you a pair of vectors, a pair of any arbitrary pair of vectors, then I can associate to this pair a number, right? I'm giving you a rule to compute a number given these two vectors. Of course, in the usual case, this number is simply the length of A times length of B times cosine of theta, where theta is this angle, right? But okay, this is just a number. It's a number which depends on both A and B, right? If I change A or if I change B, I will change this number, right? So what it is just a rule that I'm giving. For every pair of vectors, I give you a number. But it is not completely arbitrary. You see, there's a very important relation. You remember in the vector space, we have the structure of addition, right? That is the main thing. So what if I take A dot B plus C? I have two vectors B and C. So consider this here. Okay, let's say there is another vector C here, right? And I want to compute B plus C is again another vector, right? B plus C very precisely, I mean, is you draw this parallelogram, and this is B plus C. This vector is B plus C, right? Now, what is A dot B plus C? Well, this is the same as A dot B plus A dot C, right? So this is the important point, that this rule that I am giving is linear, you see, is linear in the sense that A dot B plus C is the same as A dot B plus A dot C, okay? So the scalar product has to satisfy this very important condition, okay? Then we'll again list furthermore. There are more conditions than this. This is a very important condition, but that's not all. There are more conditions. Another condition you see is that if I take A dot A, right, both the vectors are the same vector, right, then we know this is just the length square, right? This is the length square of the vector, and length square of the vector is going to be positive, right? So this is going to be greater than or equal to 0. It will be 0 only if the vector itself is 0 vector, right? Otherwise, if the vector is not 0 vector, then it will be non-zero. It will be positive. Okay. So these are some of the important properties that the scalar products satisfy. The dot products or scalar product satisfies. Okay. So this is so today what we will do is we will discuss this. This is extra structure I am giving. You see, this is more than the vector space. I am giving you one more property of this space, right? I am putting some extra information, right? But before arriving there, let me define a notion of dual vector space. And this will be useful for quantum mechanics. Probably George has already told you about dual vector space. If not, probably he will do it today, maybe. Yeah? So there's a notion of dual vector space. So this, for the dual vector space, still I'm going to use only the vector space structure, nothing more. Okay, just still I'm going to use the vector space structure. No extra features like scalar products and so on. Okay, vector space structure. So the idea here is to consider functions, linear functions. On a vector space. Okay. So what do I mean by that? So what we are saying is that there is let me use a symbol. This is not the symbol which is used in the textbook in the book, but let me just use that because F stands usually for function, right? So I will use the same symbol here, F. So this F, what it does, it maps S is a vector space. I'll always use capital S for vector space. So F maps S to real or complex numbers. So real or complex numbers. Okay. I mean, let me always work with the complex numbers because real is just a special case of it. So right. I will always work with the complex numbers. Although in these cases it will be real. I mean, this is a real vector space, right? So if the S is a real vector space, then we are looking at real functions. If S is a complex vector space, I'll be looking at complex numbers here. So let me always work with the complex because that's more general. You specialize it, you can get the real vector space. Okay. So what do I mean by that? This map. You are familiar with the notion of map. If I give you one set and there is another set, the map is that if I give you a map between one set to another set, that it says that every point here is mapped to some point there, right? And there's a rule. I'm giving a rule for the mapping. Different such mappings will give you different functions. But okay, this is arbitrary. At the moment, I just said there's a function. Function it maps. I mean, very explicitly. If take any vector A belonging to S, then F acting on A, F of A will be some number, will be some complex number. Okay. Okay. This is fine, but there is also another word here, linear. So it's not an arbitrary function, it's a linear function. Okay. So what it means? Linear means the following. If I take two vectors A and B belonging to S, then F of A plus B, right? A plus B is again another vector, and I want to ask what is the value of F for that vector. Well, that is the same as F of A plus F of B. Okay, that's a linear condition. It's a linear function. So this is the important point here. So there are some consequences immediately. For example, it tells you that the null vector F acting on the null vector should be 0. Why? This implies, you see, if I take F of A minus A, right? A minus A is null vector. Well, this is the same as F of acting on the null vector, but now use the linearity condition here. Okay. Then you find that this is the same as F acting on A. Actually, let me write it in a slightly more general. Let's put here alpha and beta. Okay. This is again a vector. Alpha and beta are two complex numbers. Okay. So now I ask the question: what is this function F acting on this vector? That is the same as alpha times F acting on this plus beta times F acting on that. Okay. Now you specialize this relation here. So you find that this is the same as f minus fa, which is 0, right? I mean, I just use this relation for, right, where b is equal to a and alpha equal to 1, beta equal to minus 1. Just use that relation. You find this, and that's 0. So it tells you the null vector is mapped to 0. Okay. That's a consequence of this linearity condition. Okay. Fine. Yeah. So now the statement is, okay, so this is a linear function. That's the definition of linear function. Now consider the set of all linear functions on a given vector space. So set of all linear functions. Okay. The claim is that the set of all linear functions on a vector space S is again a vector space. Okay. So what is so I need to define a notion of addition, because remember, it's not enough to just say the set is a vector space. That's not, doesn't make sense. You have to define a concept of addition, right? So what is the concept of addition on functions? Now you want to add two functions. Suppose I give you function f1, function f2. I need to have a notion of multiplication by numbers as well as addition, right? These are two important points which goes into the definition of vector space, right? So okay, so can I erase this part now? Okay. So now we consider, I don't know, what shall I call? Let me just use the same symbol, S tilde. Okay, S tilde is the set, the set of all linear functions on S. S is the original vector space, and I define a set. This is a set of all linear functions on S. Now I need, so let me call, so let's say f1 and f2. Suppose f1 and f2 belong to S tilde, then I need to define a notion of addition and multiplication by numbers, right? So we'll define, so suppose alpha and beta are complex numbers. Then I want to ask, I want to define what do I mean by alpha f1 plus beta f2, right? This should be again another linear function, right? Because we want, I mean, if we want to show that this is a vector space, that means there is an operation called addition which takes two elements and maps it to another element in the same set. Okay, so we want to have something which is this, I mean, that some definition such that this is again a linear function. Okay. Some definition of addition. Well, that is, so what is the definition? Well, I can define a function once I know how it acts on every element of S. I mean, after all, that's the definition of the function. If I know how a function acts on every element of the set, then I have defined the function completely, right? So what I will do, so I will define this on an arbitrary vector. So A is an arbitrary vector. So for any vector, I want to define what do I mean by this function. Well, this is an obvious definition. It is simply alpha f1 acting on A plus beta f2 acting on A. Right? So f1 acting on A is a complex number. You multiply that by alpha plus this is again another complex number times beta. This whole thing is a complex number. A very natural definition. I mean, you know, this is, you cannot think of anything else. This is the natural definition. Okay. Now you can prove immediately that this is a linear function, right? Because indeed, if you put here some, I don't know, say gamma A plus delta B, two vectors. Well, so okay, let's do this. I mean, I think let me just do it once. Then it will become very obvious. I mean, then you don't have to keep doing it all the time because it's almost intuitively clear. So I want to check whether this is linear. So we want to check. So this object alpha f1 plus beta f2 acting on, say, some gamma A plus delta B. where gamma and delta are complex numbers and A and B are arbitrary vectors of S. So I want to ask how this acts on that, right? Well, I first of all use the definition of this addition. Well, that by definition is alpha F1 acting on this argument, gamma A plus delta B plus beta F2 acting on gamma A plus delta B. Right? So here, going from here to here, I just use the basic definition that here. Right? Now I use the fact that F1 and F2 are linear, right? Yeah. So this is the same as alpha times gamma F1A, yeah, brown, plus delta F1B. That's the first term, and here plus beta gamma F2A plus delta F2B. Okay. Now let's take all the terms which depends on A together and B separately together. So here you see I can rearrange. So you get here alpha. So let's put gamma outside here. I'm just taking these two terms now, right? Because both come with a. So I take gamma out, and then here I put here alpha F1 A plus beta F2A. Okay, so that's the first term. Then similarly, I take the delta terms separately. So I get here delta and alpha F1B plus beta F2B. Okay. But this by definition is, again, I'm using the same definition here now. This is the same as, so gamma alpha F1 plus beta F2 acting on A. Right? I mean, if you open this up using this basic definition of addition, you get that first bracket. And similarly here you get plus delta and then alpha F1 plus beta F2 acting on B. Right? So you see that this definition, I mean, whatever definition we have given is again, it defines a linear function, right? Because, I mean, this acting on that should be gamma times this acting on A plus delta times this acting on B, which is indeed what we are finding. Okay. So this is a good definition. I mean, it gives you, yeah. This addition gives you a function which is again linear, so which is again in the same set, S tilde. Okay, we need to also specify what is a zero function, right? If you want to say that this is a S tilde is a vector space, you also need to have a null vector here, right? And the null vector is simply, okay, but let me see, is there any question in this steps? I mean, is there any question here? I mean, it's quite straightforward, right? Okay, so now I need to, so this is that. What can I erase that, or can I erase this? Okay, maybe shall I erase this part here? This part has not been treated in detail in the book. Okay, so maybe you should take notes of this part because it's not treated in detail. Only very briefly it is mentioned in the book. But I think George will need this for the quantum mechanics, so that's why I'm going through this. George will introduce dual vector spaces in this way. Okay, so now, so I need to define what is the null element in S tilde. So this is a question, what is it? Well, so define the null, what shall I say, let's call it 0 tilde or something, I don't know, some symbol. This is just to indicate that there is a zero function. Yeah. Acting on, by definition, acting on any vector A is simply 0. For all A, for all A belonging to S. So this is the null element of S tilde. And indeed you can see by the definition we have given for the addition. So if I take any function f and add to that the 0 tilde, right, then this acting on any object, any element, is the same as f acting on A plus 0 tilde acting on A. This is where I've used the definition of the addition I've given before, right? I defined how you add the two elements here, right? This was the definition. Okay? But 0 tilde acting on A is 0, right? For any A. Therefore, this is the same as f of A. Right? So that tells you f plus 0 tilde is the same as f, because this is true for every A. Right? So this implies that f plus 0 tilde is the same as f for any f. That was a definition of null vector, right? To take any vector and add to that null vector, you get back the same original vector, right? So this is indeed what you find. Similarly, then you can verify everything else. These definitions satisfy all the conditions that we had listed for the vector space. Okay. What is the inverse element? That's also clear. You can just take the minus f. I mean, so let's say the inverse element is inverse in the sense of addition, no? Not in the sense of division. So if f is given, then f is given. Okay, this is some number. Then let's define f prime, which is going to be the inverse of that. F prime of A is simply equal to minus f of A for every A. Then that will be the inverse, correct? Because then f plus f prime acting on A is simply equal to f of A plus f prime of A by the rule of addition, which is the same as f of A minus f of A, I've defined here, which is 0, right? Which is the same as 0 tilde acting on A. Right? So that tells me that f plus f prime is equal to 0 tilde. Okay. So and then maybe you can, I mean, maybe at home you can check that this definition satisfies all the other properties like commutative, associative, distribution, distributive laws, and so on. This satisfies everything. Okay, so the upshot is that what we have shown here is that with this rule of addition, maybe I should write down somewhere, the rule of addition was alpha f1 plus beta f2 is that function, linear function, which acting on any A is given by simply alpha f1 acting on A plus beta f2 acting on A. Okay. This is just I just write it down to remember this is the definition. Sorry? Definition for addition. I mean, as I said, this is a set. But if I want to say that this is a vector space, I need to define what do I mean by adding two functions, right? And multiplying by a complex number. So here I have given the definition. Alpha is a complex number, so I have multiplied, right? Beta is again complex number multiplied to f2. And then I have here a definition of addition of these two. So that gives you a definition of how you add. Okay. So with this rule, what we have shown is that this S tilde is a vector space. Okay. But now you can ask another question. What is the dimension of this vector space? Right? Suppose S has a dimension n. Okay. Then you can ask the question, what is the dimension of S tilde? Right? No, that is a surprising thing. Yeah. You see, remember yesterday or day before yesterday, I gave you example of infinite dimensional space. That was a space of functions, right? But those functions were not linear functions, arbitrary functions. right? I was considering arbitrary functions. Then of course it's infinite dimensional. But now I'm restricting myself to linear functions. Those are very, very special functions, right? Very special functions. No, it's a good point, because I mean, when you say function space, the first thing you think of is infinite dimensional, which is indeed, that's what happens. But this is not arbitrary function, it's a linear function. Let's take an example. Forget about this for the moment. Let me just take a simple example of just a function of x, one variable, a function of x. Okay, x is a real axis, right? X goes from minus infinity to plus infinity. Okay, is this a real line? I want to, so I consider arbitrary function f. If I consider arbitrary function x, this is of course infinite dimensional. The set of all such functions will be infinite dimensional, right? As we already took example, not on a real line, we took the example on a circle, I mean on an angle theta from 0 to 2 pi. There already we saw, if you look at the Fourier series, you have infinite number of terms, so you need to specify infinite number of coefficients to specify the function. So it's infinite dimensional space, right? Same way here. I mean, if you consider even arbitrary polynomials in x, the powers can be arbitrarily high, right? And you have to specify all those coefficients, so there will be infinite number. But now I'm specializing to linear functions. These are not arbitrary functions, linear functions, right? So what it means, so if f is linear, that means f of say x1 plus x2, two numbers, is equal to f of x1 plus f of x2, right? And then you see that this condition tells you that the only linear function is f of x is some number, let's say a times x. That is the only function which satisfies the property. If, for example, quadratic, if you take quadratic, that will not satisfy this equation, right? It's only a linear function. And moreover, you cannot even add a constant here, because remember this condition tells you that f of 0 is 0, because if I choose x2 equal to minus x1, then that will be 0. So, but if you take x equal to 0, if b was there, then this would not be true, right? So b is 0 also. So it's just this function. This is all. So it's one dimensional, because the only thing you need to specify is this constant, right? You choose different values of a, you get different linear function, right? But it's one dimensional, because you need to only specify one information, right? So yeah, that's quite, yeah, it's a bit counterintuitive, but it's because of linearity. Linearity is so strong condition. Yeah. Okay. I mean, so as I mentioned before, that I mean, you will see eventually that this notion will be tied to the scalar product. Okay. The very next step I will be talking. I will show how. Okay. This is a more abstract structure. I mean, I'm just defining dual vector space without even introducing any scalar product in the vector space, right? But if there is a scalar product in the vector space, then there is a natural. I mean, then there's a natural way to define the dual vector space. Okay, but we already saw the scalar product is linear, right? So that's why here, I mean, we are considering dual vector space. But even quite generally from that, I mean, we are trying to exploit all possible things that you can get from linearity of the vector space, right? So the vector spaces are linear, right? There is a notion of addition, linear additions, and so on. So we are using all the structures of vector spaces. So it's in that sense, yeah. Okay, so now let's see. So what is the dimension of this? So let's suppose dimension of S is n. Okay, so the original the vector space. So that means I can choose a basis here, which I denote by so 1, 2, n. Okay, so this forms a basis. A set of linearly and linearly independent vectors will form a basis of S. Okay. Then you see, to define a function, a linear function on S, it is sufficient to define the value of f for each of these basis vectors. Why? Because I know that any vector A, I can write it as some ai I summed over I, right? The fact that it is basis, this means that any arbitrary vector I can expand. I can write it as linear combinations of this. Okay. Now, f of A, if f is a linear function, is the same as that, f of sum I equal to 1 to n ai I. But now, using linearity, you see this is the same as sum I equal to 1 to n ai f acting on I. Correct. Now, these are numbers, complex numbers. These are the vectors, and this is just a sum of vectors. I mean, this is a rule I gave. No, the linearity rule was this: f of alpha A plus beta B is equal to alpha f of A plus beta f of B. Right? That's a linearity. That's a definition of linear function. Okay. So I'm just using that here. I mean, here I have just two vectors, but here you have n vectors. Right? You just repeatedly use this property, then you find it's a sum of n terms. So what is it saying? It says that it is if I just specify how f acts on the basis vectors, right, then I know how f acts on any vector, right, by this rule, you see, because any vector can be expanded in terms of basis vectors, then f acting on any vector can be expressed as linear combination of f acting on basis vectors. So if I know this, then I know how f acts on the entire S, right. So it's sufficient to specify how f acts on the basis vectors. Okay. Of course, this could be arbitrary numbers. I mean, we don't know, right? I can consider this f acting on this I could be arbitrary numbers, and of course, as I change these numbers, I will get different functions. Right? Now I will try to show that in fact S tilde also is n-dimensional, which means I can find n linearly independent function. Maximal set of linearly independent functions here is n. Okay. Any question here? No. Okay. So let me explicitly construct to you a basis for this S tilde. So I will define linear functions like this: f I, okay, where I goes from 1 to n. So how I have to define? I have to give a definition, which means, as I already proved to you, to define a function it is sufficient to say how it acts on the basis vectors, right? So I will just specify how it acts on the basis vectors, right? So I will define this acting on basis vector j. Remember, I goes from 1 to n, j goes from 1 to n. This is nothing else but Kronecker delta. You know Kronecker delta? You are familiar with this symbol? This is symbol, yeah. So this delta ij is equal to 1 when I is equal to j, and it's equal to 0 when I is not equal to j. This is a Kronecker. This is called Kronecker delta. Kronecker delta. This is a very useful symbol. It will appear all the time. So what I have done is I have done fi. Fi. This is a particular function. This labels I labels this function fi. This acts on the j. It gives you delta ij for all the j. Right? So in particular, just to explicitly write down, f1 acting on 1, and the first basis vector is 1, but f1 acting on everything else, so 2, f1 acting on 3, etc., is 0. Right? That is what I mean by here. So this defines to me one function, right? And now I can extend it to the entire vector space by using this linearity property. Right? Okay. Similarly, f2 will be F2 acting on only the second basis vector will be 1, and on everything else it is 0, right. So, this is just a definition. I have defined to you n functions. Okay. Now, the claim is that these n functions form a basis, okay, of S tilde. So, let us see. As I said, I mean any function f I can specify by just specifying its action on the basis vectors. This is arbitrary function now. F is an arbitrary function, arbitrary. I mean f belongs to S tilde, an arbitrary element, linear function, right. So, since it's a linear function, it's uniquely defined once I specify its action on basis vectors. Okay. Now, I want to express this f as a linear combinations of this fi. Okay. So, now this will be some, okay. So, I define f is equal to fi, f acting on I times fi summed over I. Okay. I mean this is some number, right. This is a complex number, right. I mean I have given you some function f inside S tilde. That means I know what these numbers are, right. Okay. So, I take this number and multiply to this fi, this basis, these functions I have defined. Okay. Now, the claim is that this is true, that this f I can express as linear combinations of fi. Let us check that. Well, if I want to apply this on, let us say a j, a vector j, a basis vector j, that is the same as here, I equal to 1 to n, f acting on I. Then fi, I mean this is just a number, complex number, right. So, now I use the rule of addition here. It's complex number times fi summed over I. So, it is the same as this complex number times fi acting on this vector and some more. Okay. So, I just use this definition in doing it here. And now I use a definition of fi the way I have defined here, that is simply delta ij, right. So, this is the same as I equal to 1 to n f I, this is a complex number times delta ij, Kronecker delta summed over this. And now you see this I am summing over I for a fixed j. I mean j is something, whatever j is a free index. If it appear in the left side, it is something fixed. Okay. So, in this sum, this will be 0 whenever I is not equal to j, right. So, all the terms in this sum when I is not equal to j will vanish, because there is a 0 multiplied by whatever number here is, right. And the only term is when I equal to j, but when I equal to j this is 1. So, you get this is the same as f acting on j, right, because I is equal to j. That is what, so you have proven that when if I consider this linear combination, then that linear combination acting on a vector j reproduces the same number as f acting on j. But j was arbitrary, I mean j was all the basis vectors. So, we are saying that this guy on every basis vector gives the same number as this guy, right. Therefore, these two are equal. So, you see you have expressed an arbitrary function f as linear combination of these n vectors here, I mean n functions here, right. Okay. Furthermore, you can also show that these functions are linearly independent. I mean it is not enough just to say that. So, what I have here shown is that every linear function can be expressed as linear combinations of these n functions, linear functions, right. But I have to also show one more thing, that these linear functions are linearly independent, right. I have to show that. And to show this, I mean to show that something is a basis, something, I mean the dimension is a maximal number of linearly independent vectors, right. But I mean it could be that these are not linearly independent, in which case the dimension would be less than n, What this says is the dimension cannot be more than n, because for sure every vector I can express as linear combinations of this n. But it might be that these themselves are not linearly independent. Maybe out of this n, only n minus 1 are linearly independent. Okay? In which case the dimension would be n minus 1. Right? So I need to also show that. So how to show this? Well, just go through this. So can you erase this now? This side. Okay. I did, because here definition is given. Okay, so let me erase this part here. Probably is enough. Okay. So we want to check whether these are linearly independent, right? So what is the definition of linear independence? Well, we just look at the equations. So choose arbitrary coefficients. I don't know what should I call it. Alpha I times fi summed over I. The question is, and I look at this, that this is null function, right? And I ask for the solutions for alpha I. If there is a non-trivial solution for alpha I, then these are linearly dependent. They are not linearly independent, right? If the only solution to this equation is all the alpha i's are equal to 0, then they are linearly independent, right? Okay. So given this, so let's apply. So this we are saying that this is equal to that, and I want to ask what are the possible values of alpha I, such that this is true. So let's apply this on a vector j, both sides on a vector j. So let's apply here I equal to 1 to n, alpha I fi acting on j. J is any basis vector. This is the left hand side gives you that. So this is the left hand side. Let's say left hand side. Well, this is simply delta ij by definition, right? That's how I have defined fi. And then again you sum over I for the same, like this, exactly the same way. This is delta ij, right? And then you sum over I. The only contribution will come when I is equal to j. When I is not equal to j, this vanishes, right? So when I is equal to j, this just gives you alpha j, right? I mean this sum. Maybe I should do it 2 steps. So this is the same as I equal to 1 to n alpha I delta ij, right? Because that was the definition of this function fi. And now I sum over I. This is 0 whenever I is not equal to j, right? So the only term which will contribute is when I is equal to j here, right? And then you get alpha j. Right? On the other hand, look at the right hand side. So right hand side, again you see I apply the left hand side on vector j. Now let's apply the right hand side on vector j. Well, that is 0. That was the definition of null vector, null function. So by equating the left and right hand side, you see alpha j is equal to 0. But that is true for every j, because this j was arbitrary. That means every single such these complex numbers is equal to 0. Therefore, these functions are linearly independent. Okay. So that's a so this is a very important point. The S tilde, which is the set of all linear functions on a vector space, has the same. First of all, it's a vector space by all these rules of addition and so on. And secondly, it has the same dimension as the original vector space. Okay. Original vector space S had n dimension n, and also S tilde now we have shown explicitly S tilde is also dimension n. Okay. So this S tilde is what is called the dual vector space. So given a vector space S, there is always a dual. You can always construct a dual vector space S tilde, which is just the set of all linear functions. Okay. It's a dual vector space. So conclusion is the dimension of S tilde is also equal to n. I mean the same as the dimension of S. Okay. As I said, in all this this entire chapter, dimension will be always finite. I'm not going to worry. I mean, it is all finite. N is finite. Infinite dimensional cases there could be subtleties. So n is finite.
because we say that the dimension is a maximum possible number of
Yes.
independent vectors in
Yes.
a set.
Yes.
When we define the base, we say that the base is also a maximum set of linearly independent vectors.
Precisely.
So what is the base the same as the dimension?
No, it's the number of elements. So I mean, so what have I done? Let's see the logic here. What I did, I defined these functions fi from I equal to 1 to n. This is the definition of those functions. These are linear functions. I have defined those. So these are all elements of S tilde. Now, two things I have shown. One, that fi are linearly independent. I mean, that was this discussion, right? They are linearly independent. Okay. The second thing I need to check is whether is it a maximal number, right? Are these a maximal set? Is it a maximal set or not? What it means that if I add to this any other function, then it should become linearly dependent, right? But we have just shown that the previous thing which I showed was that if I put any function f, so I have the list f1, f2, fn, right? These were these n functions. We know that these are linearly independent. Now we want to check whether this is a maximal, right? Which means if I put any function, any other function, include this in the set, then this should no longer be linearly independent, right? But that's what we showed, because we showed that any f can be expressed as linear combination of this, right? So if I put in any other f, this will not be linearly independent anymore, right? So this is indeed a maximal set. This is a maximal set. Okay. And what is the dimension? Dimension is the number of elements in this maximal set. Okay, that's n. Yeah. Okay. So this is called the dual vector space. This is the dual vector space. Okay, they have the same dimensionality. Now, given any two vector spaces with the same dimensionality, they are isomorphic to each other. I mean, you can give a map from one to the other. Okay, the one-to-one map you can give. So there is but there is nothing canonical about that map. I mean, you can choose. I mean, there's nothing natural about it. You can choose any map you wish. Right? I mean, when you have as an example, you could choose, for example. I have a set of basis vectors here and I have a set of basis vectors there. I could map the basis vector here to the basis vector there, right? That map will be linear map. Okay, but it's nothing particular about it because choice of basis is not unique, right? I could choose a different basis here, there will be different map. So there is nothing unique about the map. But what is true is that if I have two vector spaces which have the same dimension, right? Then you can give a one-to-one map between the two vector spaces. Right? Now, so as I said, there's nothing unique about it. However, if a scalar product is given, if a scalar product is defined in your space, then there is a natural. You can give a natural map between the dual vector space and the original vector space. Okay. So now we move to the scalar product. This is usually, I think also in the book, this is not the way it is dealt. I mean, this is not the way the dual vector space is introduced. Actually, the way it is introduced is first define the scalar product, right, and then define the dual vector space. Okay, that is the way it is done in book. But I did this way because I think George will be using this formalism, so that's why I did that. This is a little abstract, this is but okay. Okay, now let's define a scalar product. Let me see, is that what is called? Or inner product, what is it called? It is scalar product, yeah? So S is again a vector space, Okay. And so let's say if I give you, so what is it? So given any pair of vectors A and B, okay, so any pair of vectors in S, the scalar product gives you a complex number, right, as I said before, and I will use the notation BA, okay, for the scalar product. Again, I'm using the quantum mechanical bracket notation, right. So this this should satisfy. So this is a number. This is a complex number. Okay. So this is a complex. So there is. So what I'm saying is that for any pair of vectors in S, the scalar product is a rule which associates a complex number to this pair. Okay. But it should satisfy certain properties. It's not just an arbitrary such complex number. It satisfies a property. One is that there is a. So let me write down the properties that they have to satisfy. So first thing is, here you see there is a, it's not the same, BA is not the same as AB, right, the difference. But what is the relation between the two is this, BA is equal to AB complex conjugate. So this is, see, this is in general complex number. For the real vector space, it will not be different. In the real vector space, this will be real numbers, so anyway, so both will be the same. But in complex case, the relation between this and that is a complex conjugate of each other. Okay. That's one thing. Second is linearity. This is, of course, a very important thing. So if I take, let's say, if I consider, say, C, which is some alpha A plus beta B. I mean, I add these two vectors. It will be some vector. I just call it C. Then D with C, D is another vector. D, the scalar product of D with C is the same as alpha D with A plus beta D with D. Okay. This is the more or less what I mean, in the example that we were discussing for the two-dimensional case, you remember I took A dot B plus C, right? But that's the same as A dot B plus A dot C. This is the linearity condition, exactly. I mean, more generally in that example, I could have taken A dot, say, alpha B plus beta C, where alpha and beta are real numbers, because that example was real vector space. Okay, then that would be simply alpha A dot B plus beta A dot C. Right? This is exactly that linearity condition. Okay. So this is the second condition. Then you have a very important condition, the positivity. Here the condition, remember, was that the length square, A dot A, length square was greater than or equal to 0. Right? So we should have a condition like that here. And that condition is simply A with, so this is, let's say, C. I mean, the three conditions A, B, C. So any vector A with the scalar product of A with itself is greater than or equal to 0.
Excuse me.
Yeah.
This is the scalar product of D with C.
D with C, where C is this. C, I mean, whatever this is a linear combination of two vectors. It will be some vector, right? I give it a name, C. Okay.
But here, isn't it supposed to be the inner product of C with D?
So I mean, so now I'm taking the D with C. D is another vector. So there is a so C, this is a, and D is also another vector of S. So this belongs to S, and this belongs to S, and I consider the scalar product of these two. So D with C, but C is that, right? So what I have done, I mean this is the same as if I write it like this, D of acting on alpha A, I mean scalar product of this with that. Right? I just introduced C not to write it like this. No? Yeah. Okay. So the third condition is that A scalar product of A with itself is greater than or equal to 0. Well, first of all, you see already from this condition, you see if B was equal to A, that means A with A is equal to A with A bar, which means that is going to be real, right? Already this condition tells me the scalar product of A with itself is real, right? However, what this is saying is that it's not just arbitrary real, it is positive or 0, not negative. It cannot be negative. That's what this is saying. And so this is greater than or equal to 0, and if A with A is 0, then A is a null vector. As we saw in this example, I mean if the length square of a vector is 0, it is just 0 vector itself. So that is what we are saying here. Okay. Now this is not always true. I mean in physics with the vector spaces that we come across, they do satisfy these conditions, but not necessarily that. There are some cases where this is not true. Okay. In most of the cases this will be true. Most of the physics cases this will be true, but there are some cases, in particularly when we discuss when we go to special theory of relativity, this is not true. Okay. So this has to be relaxed when we discuss special theory of relativity. But for this course, we'll be always including this. Okay. So this will not cover special theory of relativity, but basically most of the other things it will cover. So this is just a caution. I mean that this can be relaxed. Okay. There are in fact physically interesting situations where this has to be relaxed. Okay, so these are the basic definitions, basic properties that this scalar product must satisfy: linearity and this positivity. Right? These conditions. Yeah. I think I should erase somewhere. Maybe I can erase this part. Actually, so now I mean this is a bit not completely. See, I said this is linear in this argument, right? Because C was that. However, what happens if I take, instead of DC, I consider CD? Remember, this is not symmetric, right? I mean, in the complex case, it's not symmetric. If I take CD, well, that's by definition just the complex conjugate of DC. I mean, from this property. If I then DC is that, which means it's complex conjugate of this whole thing. This is a complex number, so it will become alpha bar. Then complex conjugate of that will become AD. Again, I'm using this property here. So this is AD plus complex conjugate of that, so it's beta bar. And then again, complex conjugate of that will be, you can exchange, so BD. Now you see, this is, if I can take the D outside, then what we have here inside is alpha bar A plus beta bar B. Okay. So it's like in this argument, it is not linear. It is what is called antilinear. Okay. I mean, its coefficients have to become, you have to take complex conjugate of the coefficients. So here, here you see when I wrote C equal to alpha A plus beta B, dC was simply alpha, the same coefficient alpha times dA plus beta times dB. But when I do other way around, CD, right, you see what is coming out here is alpha bar, alpha bar with AD, alpha bar with AD plus beta bar with BD. So it's kind of anti-linear in this argument. Is linear in this argument, the second argument, but anti-linear in the first argument. Okay, that is yeah. Bar is I mean complex conjugate. So in other words, if any complex number alpha is a complex number, will have, I can write it as let me call it alpha real plus I times alpha imaginary, right? The real part and the imaginary part. Right? So what is alpha bar? Alpha bar is alpha real minus I alpha imaginary. I mean alpha r and alpha m are real numbers. Any complex number will be sum of, I mean a real number plus I times another real number. Right?
You mean there should be a bar on DC there. CD is a AC bar.
Ah, yeah, correct. Yeah, sure, yeah, absolutely. Thanks. Yeah, yeah, that's what I use in fact. Yeah. Okay, so this is a little. I mean, okay, this is something. This is a property of the fact that there is this relation. Now, what is the relation between? I told you that when you have a dual vector, I mean, when you have a scalar product given, then you can give a natural isomorphism, natural map between the S and S tilde, and that you can give in the following way. So you can define like this. Let me try to see how you can do this. Yeah, so you could do the following. So let's say if I take any A, B with the I, this will be some number. I is some basis. I is some basis. So let me choose I as basis vectors. Yes. So I goes from 1 to n. Okay. Then if I take any vector A, okay, and consider this, consider this object AI Fi summed over I. Remember, this Fi is what the one she had defined before. Right? What was Fi? Fi was a linear function which was this was equal to delta ij. Right? This was a linear function. So consider this. Consider this object. This is a linear function. This is an element of S tilde, because these are just complex numbers, right? And this is the function, linear functions. So sum of linear functions. So this belongs to S tilde. Okay, and what I can do is I can define a map. A is mapped to Fi of this combination. This is a map. This is S to S tilde map. It's getting very late. I mean, this thing has a property. This exactly has a property. Let's apply this object AI Fi on any function, any basis element j. This is a linear function acting on that. Then that is nothing else but AI delta ij sum I equal to 1 to n, which is the same as aj. So you see, this function acting on any basis vector j is the same as a scalar product of A with that basis vector j. Right? or more generally, if I consider some vector B, which is some combination, of course I can expand Bj, J, right, and consider A, this function AI, Fi, summed over I, acting on B, right? This is a function. This is an element of S tilde, correct? And I apply this function on this vector B. This is an arbitrary vector now, which is a linear combination of basis vectors. Okay. Then using the linearity property, this is the same as AI I equal to 1 to n. This is always, I sometimes forget to write the range, but the range is always 1 to n. This times j equal to 1 to n, and I use now the linearity. This is a linear function acting on that, but that is this linear sum. So that's the same as bj and fi acting on j, right? Fi acting on this j. Now again use the fact that this delta ij. So this is the same as sum I equal to 1 to n ai, and that is j equal to 1 to n bj delta ij. Okay. In this sum, only when j equal to I will contribute, and then you just get the bi here, right? So this is I equal to 1 to n a I bi, but that's the same as ab, right? So you see with this function, this linear function precisely is the, what is it, it plays the same role as this A in the scalar product, right? So because this is arbitrary vector B, right? This function acting on that gives you the same number as the scalar product A with B. So this is a natural map. This maps, I mean, A is a vector in the S, right? Now I have given a map to S tilde, and what this has a property. This is a property is that this element of S tilde acting on any vector is the same as the scalar product of A with that vector, right? So this is a kind of natural map. So when there is a scalar product, there is a very natural map between the S and S tilde. Okay. So this is the point. I'm going very slow actually. I was going a bit slow because the dual vector space, the way I have introduced, was a bit abstract, so I had to go very slowly in that. Okay, now okay, let me just do a couple of things before ending today. Two actually very important points here. Yeah, one is the Cauchy-Schwarz inequality. This is an important inequality. But before that, is there any question here? In this notation, you see that in quantum mechanics you have this ket and bra. No? So the ket is if there is in the original vector space, whatever, then the bra is in the dual vector space. That is what this is saying. And because this is nothing else, but as you see, it's a linear function. Okay. So it's in the dual vector space. I think George will say a bit more about this. Okay, now let's see. Let's again go back to the example of the two-dimensional example. You have two vectors, say A and B. Then we know A dot B is A, length of A times length of B times cosine theta, where theta is a sine wave. Right? Now, cosine theta, the range of cosine theta is between -1 and +1, right? After all, sine and cosine, they're all, the range of cosine theta is between -1 and +1. Correct? So, I mean, that is of course clear, because after all, theta, cosine theta is defined like this, no? If I have an angle theta, then what I do, I just draw a perpendicular from, say, here to there, right, to make a right angle triangle. This is 90 degrees. Then cosine theta is simply this length divided by that length, right? So surely this length is going to be smaller than that length. So it's going to be less than 1, right? Only case when it will become 1 is when angle theta goes to 0. In that case, this line just collapses to that line, right? Otherwise, this will be always less than 1. So this is the thing. So in particular, magnitude of cosine theta is less than or equal to 1. Okay, that's the thing. So as a result, you see that what this is saying is that if I take the magnitude of A dot B, then that's going to be less than or equal to magnitude of A, I mean the length of A times length of B, because cosine theta is always, magnitude of cosine theta is always less than or equal to 1, right? So this is a very important inequality. So the dot product of these two vectors, if you take the norm, the magnitude of that, that's going to be less than the product of the two lengths, less than or equal to product of the two lengths. It will be equal, I mean, when will that be equal? It will be equal when cosine theta is 1, +1 or -1, in which means that they are parallel, right? Either parallel or in opposite direction. That's the only time when it happens. Otherwise, if there's any non-zero, I mean non-trivial angle, it will be less. I mean, this will be inequality. Okay, so now one question we can ask is that, I mean, we have now here a much more general situation. I mean, we have even complex numbers, scalar products are even complex numbers. Do we have some such inequality? Right? This inequality is called, what is it called? Cauchy-Schwarz inequality. It's called, okay, so let me erase this. Cauchy-Schwarz inequality. So question is that can we generally prove it using the basic definition of the scalar product? I mean, this was a specific example of the real vector space where we have used this particular definition of the scalar product, right? And for this particular definition, we indeed see that this inequality is satisfied. But now we have a much more, I mean, we have a general definition, right? We are not taking a very specific example of a thing, but we just have some properties that it satisfies, right? Question is, given those properties, can we prove some such inequality? That's the question. Okay. So let's, so what we want to prove, in fact, is exactly this, that if I give you two vectors A and B in S, then you take the scalar product of these two and take the magnitude of that, okay? This is going to be less than or equal to the A with A square root times square root of B with B, right? I mean, you see this A length of A is nothing else but A dot A square, right? Square root. This is what I mean by length of A. A dot A is the length square, right? But when you say length, I have to take the square root of the length square, right? So that's what I mean. This A scalar product of A with A, since you know, but one of the conditions was that this is non-negative. That was one of the conditions we had, right? So when it is non-negative, I can of course take the square root. That will be a real number, right? Okay. So this is the question: is it true or not? Okay. In fact, it turns out this is true. That is the Cauchy-Schwarz inequality. So let me just go through the proof of that. Okay. So let's see. Okay. So consider a vector C, which is a linear combination of A and B in a very particular way. I will write it like this. So this is equal to A minus x times BA B. Okay. So let's say again, where x is a real number. X is a real number. This is complex. BA is in general complex, right? I mean, so here is a complex. This is a complex number. Whatever the scalar product is, B with A, right? That is, I mean, whatever the definition, whatever it is that. So I am taking a linear combination of A and B. The coefficient of A is 1, but the coefficient of B is minus x times this complex number. So I consider that. And now let's take the scalar product of C with itself. Okay, C is this is a definition of C. So let's just do this. So what you get here is so yeah C. So first let me do it like this: C with the C here. So A, and use the linearity, right? Minus x B A C B. Is that correct? So what I did, I keep the C as it is, and on the scat I use the fact that C is this, and then I use the linearity of the scalar product. Right? So linearity of the scalar product gives you, I mean, this C with that minus this quantity and C with B. Okay, that's right. And now I again use this fact that you remember the scalar product was antilinear with respect to this argument, right? Antilinear, right? So once again now use the antilinearity property for this thing. So you find here A minus x times the complex conjugate. I mean, x is real, so complex conjugate of x is x, right? Because x is a real number. And then here you get BA complex conjugate, and then B with A, right? That is the first term. And maybe is it? Maybe I'm doing several steps at the same time. I don't know. Maybe not clear. Okay, so let's do the thing. Okay, you remember that I showed that this. I mean, if C is alpha A plus beta B, yeah, then C with any vector D was antilinear, not linear, antilinear, which means it's alpha bar A with D plus beta bar B with D. This is the case. Whereas, I mean, so you see this linear, antilinear here, it would be linear there. In other words, D with C would be simply alpha D with A plus beta D with B. Right? In this argument, it is linear. In the first argument, it is antilinear. That is simply because these two are complex conjugate of each other. That's the reason. Okay. So now I just use this. C was that. Okay. So it is some is 1 times A and then minus this number times B. Right? Now, C is now on the first argument here. So it's going to be antilinear when I open up. Right? So, okay, the first term is simply 1. So the complex conjugate of 1 is 1. Right? So you get A with this guy, A. And the second object here, x is real. So complex conjugate of x is the same. But this is complex number in general. So its complex conjugate is okay. I just put here complex conjugate. And then B with this A. Okay. So that's what I just use this antilinearity property here. Okay. That's only the first term. I have to do the same thing with this guy. So this is okay. This is just a number, so I keep it as it is, minus x BA. And now I open this up again using the fact that C is this and that this will be antilinear. Okay. So, you find here, okay, first term is simply A with B, and second term is minus x times the complex conjugate of that times B with B, right? Okay. That's what we have. So, now we can just assemble, there are 4 terms here. So, let us just assemble them together. So, okay. So, the first one term is simply A with A, and then there are 2 terms which are linear in x. This term is linear in x, right? And the first, this one is linear in x. Okay. That guy is quadratic in x, because you see this is a bracket here. I mean, this object is multiplying both the terms. So, there is a one term which is quadratic in x. But the linear term, let us assemble the linear term. So, that is minus x. Okay. So, here it is BA complex conjugate times BA. So, it is mod square. So, BA mod square. And this is also because AB after all is the complex conjugate is the same as BA complex conjugate, right. So, this is also the same. So, it is actually a factor of 2 here. They just add up. Factor of 2. And finally, we have the quadratic piece, which is x square times you have again BA mod square times BB. Did I make any mistake here? No, I think it's okay. Okay, so that is what the scalar product of C with itself is. All I've done is I've just calculating this C with C is equal to that. Right? I mean, there are several steps. This is equal to that, and finally is equal to that. So this is C with C. Okay. But one of the property of the scalar product was this is non-negative. A scalar product of any vector with itself is going to be greater than or equal to 0, right. So, since this is greater than or equal to 0, this must be greater than or equal to 0, because these two are equal. So, the important point we are saying is that this combination is greater than or equal to 0. For any x was any real number. But look at this. I mean, this does depend on x. This is a function of x, right? But we are saying that this is some function of x in such a way that this is always greater than or equal to 0. Okay. But now, how is that possible? Let's see. Let us try to see when this can be 0. Okay. Let's try to see when this could be 0. This is a quadratic polynomial in x, right. So, I can try to solve for x, right. So, let's look at this as remember the quadratic, in general if I have a quadratic equation ax square plus bx plus c equal to 0 for the quadratic equation, the solutions are what? There are 2 solutions, and the solutions are simply x equal to minus b plus minus square root of b square minus 4ac divided by 2a, right. These are the 2 solutions of the quadratic equation, right. So, now let us see what does that mean there. So, for this particular case, again it is a quadratic equation. I mean, so I want to say when this can be 0, right. We see this is greater than or equal to 0. Let us look at when this will be 0. If this is 0, then x must satisfy this solution. It must be a solution of this quadratic equation, right. So, what should be x then? X should be minus b, which is the coefficient of linear term, which is 2 ba square, right, plus minus square root of 4 ba mod to the 4 b square minus 4 times the product of a quadratic coefficient of a quadratic term with this term, right? So which is sorry, BA square times BB times AA. Okay, this all thing is square root divided by 2 times A, 2 times this coefficient. So 2 times BA square BB. Okay. So we can simplify this expression a bit. We can take out 4BA square, right, from here. So is it better to, yeah, okay, 4BA square, then you get, okay, just to simplify a little bit. So and the 2BA also, actually I can take out 4BA to the 4 outside. Yeah? Take out. No, let me not do that. Let me just keep this. Perhaps I should say something here. I mean, I will assume that the scalar product of B with A is not 0. Okay. I mean, you see, remember what we wanted to prove. We wanted to prove this inequality is less than or equal to square root of BB and times square root of AA. Okay. Well, if the scalar product of B with A was 0, then this is a triviality, nothing to prove here, right? Because for sure this is non-negative, right? If this is 0, 0 is all, less than or equal to something non-negative, right? So there's nothing to prove if this was 0, right? So the only non-trivial thing is when this is not 0, right? So I will assume that this is not 0, because if it is 0, there's nothing to prove. It's obvious, right? So the reason is because there are these things appear in the denominator. If it was 0, it doesn't make sense, right? So I will assume that scalar product of B with A is not 0, right? Because that is the only non-trivial case where I have to check anything, right? Okay. So in such a case that I can just take out BA to the 4BA to the 4 outside. So all this cancels out. So then you find here 1 plus minus square root of 1 minus BB AA divided by BA square. This whole thing divided by BB. Okay. I mean, I just took out this took out from here. So when I take it out of the square root, I'll get this becomes 2 times this mod square, which also is appearing here and also appears there. So I can cancel all that. But then once I take it out, this becomes 1, right? But there I have to divide by this. So 4 cancels, 2 powers cancel, but then there is extra 2 powers here. So that's okay. So fine, this is fine. Now, okay. So in fact, let's try to plot this. Let's try to plot this function. In general, let's try to plot this function here. I mean, okay, that's just a specific. If I try to plot this function, what are the possibilities? So I'm plotting this function as a function of x. It's a quadratic function, right? Okay. If this equation, so let me call this function f of x. Okay, this is a quadratic function. So I'm plotting f of x versus x. Okay. If this quadratic solution had some root, had a real root, I mean, this need not be real. If b square is less than 4ac, this will be negative, right? And then square root of a negative number will be imaginary, so it will not be real, right? So what I'm saying is that suppose it was real, suppose this was real, then when I plot it, at some point this function should become 0, right? I mean, so say there are 2 roots, x equal to x1 and x2, 2 real roots, then at the x1 this function must become 0, because that is actually at value x1 this f of x is 0, right? In fact, that's how we solved, right? Is that, I'm saying, forget this. Okay, this is what this solution, these roots are the solution of fx equal to 0 condition, right? So precisely at this value f of x will be 0, right? Okay, I call these two solutions as x1 and x2, right? Then at x1 this function will become 0, right? And similarly at x2 this should be 0. But what about between x1 and x2? So let's say here it is like that, here it is like that, but between x1 and x2 this will become negative by continuing, right? I mean, this is a continuous function of x, right? So if it's going like that, it's going to continue. It won't be just suddenly go up like that, right? It is a continuous function. Okay. So this will come down and go there, right? So there is, so on the other hand, I know that this object is always greater than or equal to 0, right? So you cannot have two different real roots. If you have two different real roots, then in between those two different real roots it will become negative. This function will become negative, right? Okay. However, it could happen that there is only one real, because sometimes I mean there could be degenerate roots, right? For example, if this was 0, if this quantity was 0, both the roots coincide, because plus minus doesn't make any difference, right? If there is only one root, it's okay, because then, so if x1 equal to x2, then there is no problem, because in the plot you will have something like this, because there is just one place where it is 0.
Okay.
Yeah, that will not contradict this inequality, right? So the possibilities for this to be true, I must have either two equal real roots, I mean the real roots are equal, or there is no real root. If there is no real root, then of course the plot would be, I mean it will never become 0. Then x, I'm taking x to be real, right? X for the real x, f of x will never be 0, so it will always stay up. Yeah. Of course, now here in this thing I have assumed something. I've always assumed like this, that far away for large x this is positive, and for let's say, okay, for large positive x it's positive, and this x minus infinity all the way, right? I mean this from minus infinity to plus infinity. For both x equal to minus infinity and x equal to plus infinity, it's positive. How do I know that? It could have been the other way around, no? See, I mean, how shall I say it? Okay, maybe I can erase here. Just see. I mean, here I tried to plot, assuming that f of x, that plot was for f of x for large x was positive for large x large, right? X going to infinity, the magnitude of x going to infinity. So x could be plus infinity or minus infinity. That is this plot. That is the plot I drew. So here is x1 and x2, two roots. If there are two real roots, the picture will be something like this. If the two roots are equal, then the picture will be like this. Right? This is when x1 equal to x2, and when when there is no real root, then the picture will be always up, right? It will never cross the axis. But what if it was the other way around? Suppose f of x was negative for x large, okay? Then the picture would be exactly inverted, right? In that case, the picture would be, if f of x was negative for large x, then the picture would be exactly the inverted. So if no real root, it will be always like that, right? Negative. If you have two real roots, x1 and x2, then the picture would be like this. So this is x1 x2. And finally, if the two roots coincide, the picture would be like this. This is when x1 equal to x2, right? So we need to check whether because I mean, after all, we want to prove that it is positive, I mean non-negative. So it's not this situation; it should be that situation, right? But that's easy to see because when x is large, clearly the quadratic term dominates, right? And the coefficient of the quadratic term is positive. See, this is mod square, so it's positive, and this is also non-negative, right? So it is indeed true. We are in this situation, not that situation. Okay, it's positive for the large x. It's positive. When x is large, clearly you agree, right? X square dominates. X square is much larger than linear term x or constant term when x is large. Yeah? So this is indeed we are in this situation. So the only thing that we have to make sure to prove this inequality, to satisfy this inequality, is that we should not have two distinct real roots, right? Either the two real roots are equal, meaning this situation, or there is no real root, right? But that means if you go back here, this square root, I mean either this what is inside the square root is negative, right? In this case this will be imaginary, so it will be no real root, or it could be 0. If it is 0, the plus and minus doesn't make anything. We are in this situation, right? But if this is positive, then we will be in this situation, right? And then we will violate this condition in some region for some values of x between x1 and x2. This will become negative, so it will violate this condition, right? So therefore, we conclude that for this condition to be satisfied, we must have that this is less than or equal to 0, right? Less than or equal to 0. So for this to be true, we must have 1 minus this quantity be a square is less than or equal to 0, right? So when it is strictly less than 0, we are in this situation. When it is equal to 0, we are in that situation, right? So we will not be in this situation. Okay, so now you can take this on the other side, or so this implies less than, no?
Yeah, because if it's less than,
Then it will be imaginary, yeah. Then the square root will be imaginary, so it will be complex numbers. The roots will be complex numbers, yeah. So this is less than or equal to 0. So now let's take it. Well, we can take this on the other side and multiply by BA square. Remember, we have already assumed that BA is not 0. Okay. So what this implies is that BA square is less than or equal to the product BB times AA. That was exactly the Cauchy-Schwarz inequality. I mean, just take the square root on both sides. Okay. This is just, I mean, you take this on the other side. So 1 is less than or equal to this quantity, and then you multiply both sides this by this. So you get that. Okay. So the idea of the proof was that we started with this vector C, which was a linear combination of A and B, where with some coefficient x, real coefficient x, right? And then we went through this. C was this A minus x B A B. And we took the length square of C, I mean the C product, scalar product of C with itself, that was equal to this, but by the condition of the scalar product, that must be greater than or equal to 0, right? However, we see that that can be satisfied only if this condition is satisfied, only if the x does not have two distinct real roots. Either it has no real root, or both the real roots are the same. That is the only case when this will be satisfied, right? And that condition was this condition. So you see that you can prove the Cauchy-Schwarz inequality in complete generality. I mean, just using those basic properties of the scalar product. Right? We are not assuming anything more than that. Just the basic property of the scalar product. Yeah, maybe I should. I mean, there is one more thing I would have liked to do, but I think it's getting late. Is also the triangular inequality. You know that there is a triangular inequality, right? If you have two vectors and the sum of the two vectors, right? Then the length of the sum of the two vectors is less than or equal to the length of the sum of the lengths of the two vectors, right? There's a triangular inequality, right? That also that also I wanted to prove, but I think I will do it now next time because it's getting late. These are all properties of the scalar product, essentially. Yeah, okay. I think stop here. Any questions on this? This was a little involved, I suppose, a little this proof. I mean, it was really, you had to draw these pictures to see how the behavior of this function, quadratic polynomial, right? But okay, that's. This is a very important thing in quantum mechanics. I mean, it has a very deep meaning in quantum mechanics, no? Because I mean, if you think of this is a quantum state, and you take the scalar product of these two states, I mean the bracket notation. This gives you a probability amplitude of a state. What is the probability amplitude that the state A goes to state B, for example? And this one is just the norm of A, norm of the state. You can normalize it to 1, right? Similarly, state B can be normalized to 1. Okay. Usually you normalize the state to 1. So this will be 1. But then what this is saying, that the probability amplitude of A going to a particular state B is less than or equal to 1. But that cannot be greater than 1, right? How can it be, right? That will be a violation of the basic notion of probability, right? A state can go into many different possible states. But so probability amplitude for each of these, I mean, this state going to a particular state here is going to be less than or equal to 1, cannot be greater than 1, right? So this has that meaning. It's a very important inequality in quantum mechanics. Yeah. Okay, so I stop now. Yeah.